In this video, I'm going to go through the entire lesson of expected value. So you'll be pausing partway through it, trying to practice some problems on your own. And hopefully this gives you just a little bit more clarification on what expected value is and how to calculate it. So the whole objective to today's lesson is to be able to determine what we expect out of a certain event. We're going to use a specific formula that will help us there. It's kind of a common sense formula. After you use it a while, it makes a little bit more sense than it does initially. But first of all, what is expected value? Expected value is a number that represents the average payoff for a specific game, if you will, or event. If you're rolling a die, what should we expect from that? We'll go through several of these. In order to calculate it, first what we have to do is multiply each of the payouts by the probability of getting that event to occur. Okay, and we'll kind of get into a little bit more of that. It sounds a little bit confusing right now, but we'll get into a little bit more of that. And finally, if the game costs anything to play, that needs to be subtracted out from whatever our final answer is. All right, here is the actual formula for expected value, and this looks like a large formula, fairly complicated. The formulas, the way this looks to me, looks much more complicated than it actually is. I typically don't recommend that that you write this down or do any of that. Let's do a couple, then you can always come back to this. Remember this spot in the video, and then you can come back to it if you want to and try to do it. But let's kind of go through it here. Let's start with an example problem. It says that you have a die, and we receive $1 for each point that shows. And when we talk about points on a die, a typical normal standard die has 6 sides. 1 through 6 are what the numbers are. So if you roll a 4, you get $4. If you roll a 6, you get $6. That's what we're talking about here. Okay, so in order to calculate what expected value is, what we're going to do is determine what our expected payout is going to be. So let's start from the bottom. So let's say we roll a 1. Our expected payout on that one is going to be 1. So here's our expected value formula. Let's do the 1 here for 1. The expected value is going to be 1, and we're going to multiply that by the probability of getting 1. So there are 6 sides to a particular die. So the probability of rolling a 1 is 1/6. So we're going to multiply the payout, $1, 1 for each point. It shows a point of 1, so $1 is going to be our payout. 1 times that probability, which would be 1/6. Okay, now that's what our payout would be if we rolled a 1. It would be 1 times 1/6. Well, we can also roll a 2. So the expected payout on that one is going to be 2 times the probability of rolling a 2. Again, it would be 1/6. That's one side on a die is 2 out of 6 total sides. So what we're going to do here is we're going to add that to whatever this expected payout is. So 2 times 1/6. Now then we also have 3, and the probability of rolling a 3 is 1/6. We have a 4. The probability of rolling a 4 is 1/6. All of these end up being 1/6 probabilities. But that's how much we're going to get, because if we roll a 4, we're going to get $4. So if we go ahead and continue this pattern, if we roll a 1 times 1/6, then plus 2, because we'd receive $2 times 1/6, it'd be plus 3 times 1/6, plus 4 times 1/6, all the way down. You'd end up just like this. And this is $1 for every point value that shows. So this one says if you roll a 4, you get $4 times the probability of rolling a 4. If you get 6, you get $6 times the probability of rolling a 6, which would be 1/6. Then all you need to do is type all that into your calculator. If you wanted to do it by hand, it would simplify to 21/6, which is really just 3.5. 3.5 will work perfect. Okay, now I'm going to give you one on the next one, and I'm going to have you calculate it. And then, so I'm going to have you push pause, then you come back after you've got it a little bit. It'll take some practice on these. I don't believe these to be too difficult, but they do require a little bit of practice. So let's do these two right here. Whenever you're ready, go ahead and push pause, and when you're done, come back and we'll go through it. Okay, this one you rolled. If you rolled a 5, or if James, excuse me, rolled a 5, so we go. He gets $9. So 9 would be our expected value times 1/6, because his probability of rolling a 5 is 1/6. Otherwise, he loses $1. So that's why we do our minus here. He loses $1. Minus 5/6, because there are 5 possibilities in which he will lose. So 1 times 1/6, or excuse me, 9, this is the amount of payoff. Then the probability of rolling a 5 is 1/6. We're going to subtract $1 here because he'll lose $1 if he rolls anything else. Times the probability of rolling anything else is 5/6. So then we're just going to simplify this. It simplifies to 4/6, which is 0.667. I asked to round this one to the nearest thousand, so 3 decimals. This one is really similar to this one, only you win $5 if you get a tails, and you lose $1 if you get heads. So 5 times the probability of flipping a coin and having it land on tails, minus 1 because Alex is going to lose $1 if the coin lands on heads. So the expected value is 2 on this one, meaning if we did this event numerous times, time and time again, we would expect to receive an average of $2 every time we flip that coin. All right, now let's look at this one. I'm going to have you go ahead and try these two. Whenever you're ready, push pause, then come back as soon as you've figured out the problem. Now this one here, the slugs are important. A $1 coin means that it's a $1 value. A slug is like, back in the day, they would take a piece of metal and hammer it out, so it was the exact same size as a quarter. Seems a little silly today, but you don't really see them too much today, but basically it's the same size and shape as a dollar, but it has no value. So that's going to be the important piece here. So if we calculated both of those, here's what our values would end up being. Notice down here I have listed 2 different ways you could do this one. If you wanted to, you have $1 that you would earn. The probability of getting that is 3 divided by 7. Then we're going to subtract the quarter that it cost us to actually play the game. So there you go. Otherwise, you could actually take out that, factor this 25 cents into each of these plays here. That would be $1 here. Minus 25 cents, which would mean you would gain 75 cents 3 out of 7 times, and then otherwise you would lose 25 cents 4 out of 7 times. Either way there is okay. If you got the one over here on the left, that'll be just fine. It'll work every time. If you did the one over here on the right, that's fine too. That will work as well. Okay, now we're going to pull this one up, and I'm going to kind of go through this one with you. So let's try number 1 first. The bag contains 8 white balls and 2 black balls. Aubrey picks 2 balls at random if she wins $5 if she does not pick a black ball. So that's important to know. If she does not pick a black ball, she wins $5, meaning both balls must be white. Okay, so with our expected value, we calculate what the payout is going to be. The payout is going to be $5. Okay, so she's going to receive $5. So we'll put that down. Now we have to multiply that by the probability she's going to pull out two white balls. Well, and she's going to pull them out one at a time, so let's calculate that. The probability that she pulls out a white ball, let's see, there are 8 white balls and 10 total. 8 plus 2 black balls here. So 8 divided by 10 is her probability that the first one is going to be a white ball. So we multiply those two together. But that's only the probability that she's going to pull out a white ball one time. If she pulls out a white ball twice, that means we've got to multiply this by the probability of pulling out a white ball yet again. So she already pulled out 1. That means there are only 9 left, of which 7 of them are going to be white, because one of the white balls was just drawn right here. So we go ahead and multiply that by the probability she's going to pull out the white ball the second time, which would be 7/9. Whoops, let me get that out of your way. 7/9, we just type that into our calculator. You'll find out that the expected value is 3.11. All right, so that is our expected value for that one. Now this one down here I want to go through with you as well. Liz is purchasing some risky stock for $6 a share. She estimates the probability the stock will rise to $19 a share is 0.1, and the probability that it will fall to $2 a share is 0.9. So if that's the only criterion for her decision, did she make a good decision? What's her expected payout? So let's look at this. We got to figure out how much she's expected to gain. If she is expected to gain $19 is the price that it will go up to. Okay, so if she buys it for $6 and it goes up to $19, that means she's going to make $13. Okay, she will have a gain of $13. Now we're going to take that and multiply that by the probability of her getting that, which is 0.1. We'll do that next here in just a minute. But now let's calculate how much money she'll lose if it goes down. Well, it might go down, and if it goes down, it'll go down to $2. So now we have to figure out how much she's going to lose. If she buys it for $6 and it goes down to $2, that means she loses $4 a share. So 6 minus 2 is $4. $4 a share is what she'll lose. So now, using our expected value formula, we're going to plug all that in. So here's what we've got here. This 13 right here is the expected payout. That's if it goes up, times 0.1. 0.1 is what we got right here. This was our probability that the shares were going to go up $13 each. Then this $4 is a loss. She loses $4. So that's why we do a subtract 4 here. Times the probability that's going to happen is 0.9. Now then, we're going to just simplify that, plug that all into your calculator. You'll get negative 2.3. Her expected value is to lose money on this stock trade. So it does not make sense. She did not make a wise investment with this one. All right, now I'm going to give you two to work on right now. Go ahead and try these two. When you are done with it, push pause now. When you're done, come on back, and then we'll go through the answers. Check your answers here. Hopefully you found out that she did make a wise investment on this one here. The probability that it was going to go up and how much it was going to go up was to her advantage on this one. Alright, let's try another one now. We haven't really gone through these, but hopefully you can use your knowledge of expected value in that formula to get the right answer here. So go ahead and try this one, push pause, then come back and check your answers. Check your answers here. It ended up being a positive expected value. In other words, if they didn't charge anything to play this game, it was good. It was to your advantage to play it. But as soon as they start charging here, depending on how much they charge, if they charged $2 to play that game, now it became a negative expected value, so it's not to your advantage to play this game. And you notice here, this is the exact same formula that I've got up here. The only difference is that I just hit -2 at the very end, because that's how much it costs to play the game. You could have taken $2 out of each one of these. That would work. Then you have to go -2 times however many are left, which would be, looks like 78 over 100. That would work too. Just take off 2. This would be 8 times 10 over 100 plus 3 times 10 over 100. Right here would be the tricky part. -52 is what it should have said if you chose to do it that way. Times 2 over 100 minus 2 times 78 over 100. That would have worked as well. You would have gotten the same exact answer. So if you did it this way, I find this way to be easier. If you did it that way, then that's perfect. I would continue to do it that way. All right, let's try these two. Go ahead and try this, and then push pause right now, and then come back whenever you're ready. Here you go, and this one was almost an identical problem to one that we just did. The difference here is instead of envelopes, you are drawing cards out of a standard deck. So you've got to know how many aces there are in a standard deck. There are 4 aces in a standard deck. We're going to pay out $30 for each ace. Subtract $1 for every other card that you have, which is 48. 48 out of 52. We'll subtract, you'll lose $1. And then 50 cents is what it costs to do the actual game. And similar here, both of these are rounded to the nearest thousandths, which is 3 decimals. Similar here, the only difference is you have to pay $1 to play the game, so all I had to change here was this last number. That was it. Okay, now on this one here, we're going to go through number 1. I'm going to have you do number 2. So number 1 says a bag contains 2 $1 coins and 6 slugs. Remember, a slug has no value, but you can't tell the difference. Okay, so if you reached your hand in there, you would know which one was a slug and which one was an actual dollar coin. Okay, so you reach your hand into the bag and you get to keep what you pull out. So we want to determine the fair price of the game. That means when the expected value would be 0. What we can charge for this game so that if you played it numerous times, you would end up with an expected value of 0. So let's plug this into our expected value formula. So this is going to be 1 times the probability of pulling out a $1 coin. So this would be 2 $1 coins and 6 slugs. So this would be 2 over 8. Okay? 1 times 2 over 8 minus whatever the cost is. That's the thing that we're trying to find right now. Would equal 0. Now remember, this is considered the fair price for playing the game. We want our expected cost, or the cost on it, the expected value I should say, to be 0. So we're trying to determine the cost. So now what we're going to do is just solve this one for cost. If you want to, and it makes it easier for you, instead of writing cost, you can write x. Then we just solve it for x, and that would work too. Okay, so this one will give you 0.25 minus cost. It would equal 0. Some of you can quickly identify that the answer is just your cost should be a quarter, 0.25. If you want to think of it mathematically, it may be a little bit easier to think of it like this. If it were an x, 0.25 minus x equals 0, what are we going to do? How are we going to solve that one so that we can isolate x, get x all by itself? So we would end up adding x to both sides. So we're going to do something similar here. All we're going to do is add the cost to both sides. And if we added the cost to both sides, we'd find out that the cost was 25 cents. That should be our fair price for playing this game. Okay, now you try number 2. Push pause now, and then when you're ready, come on back. The cost for number 2 should have been $1 is what you should have charged. You win $13 if you draw a king. There are a total of 4 kings. So this, the expected payout would be 13, only if you get a king though. So it means our cost would be $1. $1 would be the fair price we should charge for that game. Okay, these are the final 2 that we're going to do for this lesson. Go ahead and push pause now and then come on back after you've got your answers for these 2. Check your answer for these 2. Hopefully you're starting to kind of get the feel for it. That will conclude this lesson. If you need to, you can rewind and go through any part of that you need. I also have other videos on YouTube for specific ones. If you want just a little extra practice, that will be fine too.